Good morning, students. Welcome back to our physics classes. So, during the last class, we have started with thermodynamics and we have defined what is thermodynamics. In thermodynamics, we are dealing with the effect of heat in a system. That means what heat energy can do with the system. We have defined what is a system, what is surroundings, what is an isolated system, then what do you mean by a thermodynamical state, how you can change a thermodynamical state or how you can define a particular thermodynamical state. All these matters we have already seen in the last class. And we have stopped the chapter with the concept of heat, work and internal energy. We stopped with the content heat, work and internal energy. So we have derived or we have mentioned a relation between work and heat. That means calorie and joule. How you can equate calorie with joule. That the concept that we have stopped with in the last class. And now we are going to talk about some changes taking place within a thermodynamical system. And I already told you, when I say a thermodynamical system, it is an ideal gas. It is a system of ideal gas. So, suppose you are having an ideal gas taken in a cylinder. We are having a cylinder and an ideal gas is taken in the cylinder. So, its side walls are perfectly isolating. That means no heat transfer taking place through the side walls, and the bottom is in isothermal one. That means through bottom only heat transfer is possible, and it is fitted with a movable piston, and this piston is also an adiabatic piston, and it contains a ideal gas. It contains an ideal gas at the system, and its state is given by P1, V1, T1. That is, its pressure, volume and temperature are given by P1, V1 and T1. And suppose some weights are placed over this piston, which means this piston can't move up by itself because a weight is added on the. So when a pressure P is acting from the system, that means ideal gas, this pressure will be acting on this piston also. But when the weights are placed on the piston can't move in the upward direction. That means that pressure is not doing any work there. Suppose suppose the area of cross section of the piston is A. A is the area of cross section of the piston. So when you are removing the weights from the piston, what will happen if the pressure is sufficiently enough to move the piston back, that is in the upward direction, it will move up. So to move the piston back, the system has to expand. What is the system? Ideal gas. So that ideal gas has to expand. The gaseous system has to expand so as to move the piston back. One more thing, to move the piston back, that means in the upward direction, the system has to do a work. And how much work is required? That work done you can calculate as dW for making a small displacement. Suppose it is moving by a small distance dx in the upward direction. So dW is equal to F into dx. dW is equal to F into dx. What is F here? No force is direct acting there, but we can say that the pressure P1 is acting there. Simply we can call it as PVTs. So the pressure P is acting on the surface area A. So the force will be P into A into dx. dW will be P into A into dx. So we can say that P into A dx. What is A into dx. A is the area, dx is change in length. That means this is a change in volume. So that will become P into dV. That is dW is equal to P into dV. Actually, what is this dW? This dW is the work done by the system to expand. Work done by the system to expand. That is getting as P into dV. Pressure into change in volume. Pressure into change in volume. So we are saying that at the same, when it is moving or it is increasing the volume by dV, the pressure remains constant. We will come to that. Means when this is changing its volume, initial volume V1 to a volume V2. What is the total work required there? What is the total work required there? For that, W is equal to integral V1 to V2 P dV, which is equal to P into V2 minus V1. If the pressure is taken as constant. If the pressure is taken as constant. So we can say that W is equal to P dV within the limit V1 to V2. P dV from V1 to V2. This is the general equation for the work done in expanding or work done in expansion. So when a system expands from V1 to V2, how much work is required? That W is equal to P dV. Okay. In the other words, suppose you are adding more weights over there. What will happen? The piston will move down, then it will get compressed. If it is moving from V1 to V2, then also this will be changing volume means volume decreases. That is final volume minus initial volume. Final volume minus initial volume will become negative. So in that sense, work done can be taken as negative. When it expands, work done is positive. Compress, the work done is negative in terms of volume. Anyhow, in compression or expansion, the work done is given by this equation. W is equal to integral P dV from V1 to V2. That is the work done in expanding. But remember, this work done can be taken as either positive or negative. Work done can be taken either positive or negative. See, here we have said that when the gas expands, means work is done by the gas. In that sense, when you are talking in terms of volume, if the volume increases, then the work done is positive. If it is getting compressed means the volume decreases. Then you can say that the work done is negative in the aspect of volume. But you remember that when the system expands, the system is doing a work by virtue of its own energy. Is it? No heat is applied or no another help is there. The system expands by its own internal energy, by its own energy. So what will happen? Its energy decreases. So in the aspect of energy, if the work is done by the system, it is negative. In the aspect of volume, if the work is done by the system, it is expansion and that is positive. Don't get confused. In terms of volume, work done by the system is positive, work done on the system is negative. In terms of energy, work done by the system is negative and work done on the system is positive. Work done on the system is positive means if the work is done on the system, its internal energy increases. Its energy increases. So, it is positive. That means gaining energy. And when the system expands, it is losing energy. So, work done by the system in aspect of energy. Work done by the system is negative, work done on the system is positive. In the point of view of volume, work done by the system is positive and work done on the system is negative. Okay. So remember in which aspect you are taking the work done. Work done by or work done on, whether it is in the aspect of energy or volume. That depends, that determines whether it is positive or negative. Okay, so work done on the system is positive in terms of energy, work done by the system is negative in terms of energy. Remember that. So here we can see that when the system expands, if the pressure is remaining constant, then its volume and temperature will change. Which means it is not possible that, I already told you PVTs are state variables. So it is not possible to vary any one or only one of these three variables. If one changes, if any one of it is changes, another one is also changing with that, keeping the third one constant. If pressure remains constant, volume and temperature will vary. If volume remains constant, pressure and temperature will vary. If the temperature remains constant, pressure and volume can vary or should vary. Anyhow, here the system expands, then the volume automatically changes. Obviously, volume changes. If the volume changes, we can say that one of its state variable changed. If any one of the state variable changed, automatically other one is also changing. We are not talking about that, but we can say that if any one of the state variable is changed, then the system changes its state from one to another. That means a process had happened. A process happened when any one of the variable changes. Okay, so here the process changed, happened when the volume changes. Suppose the temperature remains constant, which means no heat is transferred to, no heat transfer is there. So, which means its temperature remains constant. And pressure and, we can't say that no heat is transferred there and the temperature remains constant. Bottom is an isothermal one. And if the volume changes, automatically the pressure decreases. When the temperature remains constant. That only we can say that. If the temperature remains constant, as the volume increases, the pressure decreases. That means at constant temperature, pressure and volume are inversely proportional. So anyhow, we can say that process, that means thermodynamical process, can be expressed with the help of graph. Any thermodynamical process that we can express with the help of a graph. And that graph is known as PV diagram. That is known as PV diagram. That is pressure volume diagram. So here pressure is taken along the y-axis, and volume is taken along the x-axis. Initially, the volume you can say V1, and finally it changes to V2. Changes to P2. Since the pressure remains same, we will have a straight line parallel to volume axis. So volume changes from V1 to V2, keeping the pressure constant. Now, when you calculate the area under this curve, PV diagram, which will become P into V2 minus V1. What is that? P into V2 minus V1 will be work done, which is equal to work done. Okay, suppose pressure is not constant. Volume changes from V1 to V2, and the pressure is also changing from P1 to P2. See, as the volume increases from V1 to V2, pressure decreases from V1 to P2. So what is the area under this curve? This will be the area under this curve. How you can find it out? You can make use integration. so that is W or the area under the curve, delta A, or simply the area is equal to integral P dV from V1 to V2. Integral P dV from V1 to V2. This is, and these two are the hint that we can get from the PV diagram. That means area under the PV diagram gives the work done in that process. Area under the PV diagram gives the work done in that thermodynamic process. Okay. From the above two diagrams, it is clear that work done by the system or work done in a thermodynamical process, it is not depending upon the initial point and the final point, that is initial state and final state. Because from V1 to V2, it can vary from like this, or this is a state A and state B, and it can be through another path. So the state change, work done in a state change is not only depending upon the initial and final state, but depending upon the path through which the work done is taking place. Work done is taking place. And I will show you an example. Suppose a system is in its initial state A and it is changing to the state B through a path 1. What happens is Q1 amount of heat is supplied to the system A. Q1 amount of heat is supplied to the system A. And it does a work W1 and it changes its state from A to B. Then you can calculate Q1 minus W1, which is X. So heat supplied and work done by the system. System is taken back to the system in state A itself, and it is supplied with the heat energy Q2, and it does a work W2. Then it comes to the same final state B. Again, Q2 minus W2 we calculated, that is also found to be X. It is taken from A to B through another path by taking Q3 amount of heat and doing a work W3 reaching the state B. There also you can take Q3 minus W3 again, that is X, which means always the heat supplied and the work done by the system, the difference remains a constant, and this difference is known as the internal energy. That is the internal. We discussed what is internal energy in the last class. So this defines the definition of internal energy. That is energy stored within the system. Whatever may be the heat supplied, it stores its internal energy, and the remaining one only giving to do the work. Then only that heat supplied and the work done, the difference will remain the same. That is the importance of internal energy. Okay. One more thing that we can infer from this is Q1 minus W1 is equal to X. Q2 minus W2 equal to X. Q3 minus W3 equal to X. What it means? Q1 W1 is the property of first path, Q2 W2 is the property of second path, and Q3 W3 is the property of third path. Through any path you can take the system from A to B. It doesn't matter, but the change in internal energy remains the same. The change in internal energy. Sorry, X is delta change in internal energy. That will remain the same. So change in internal energy is a state function, it is not a path function. Work done by or work done on the system or work done in a thermodynamical process is not a state function, it is a path function. But here, internal energy change in internal energy is not depending upon the path, it is depending upon only the initial state and final state. So we can say that it is a state function. Okay? And we can say that when you are supplying Q amount of heat into a system, that is used for two purposes. One is doing work. A part of it is used for doing work, and the other part is used for internal energy change. So Q, you can say that, which is equal to dW plus dU. D, change in heat energy. That means heat energy supply dQ is equal to dU plus dW. That is termed as the first law of thermodynamics. That is dQ is equal to dW plus dU. dQ is equal to dW plus dU. Or dU is equal to Q minus W. dU is equal to Q minus W. Change in internal energy is the difference between heat supplied to a system and the work done by the system. If heat is supplied to a system, it is capable of doing the work. How much work is done? The rest is stored as the change in internal energy. So dU is equal to Q minus W, that is the, or dQ is equal to dU plus dW, or Q is equal to U plus W, Q is equal to W plus delta U. Very different forms of first law of thermodynamics is there, but the concept is same. That means heat energy supplied to a system is used for two purposes: doing a work plus changing its internal energy. So that is the first law of thermodynamics. Statement for the first law of thermodynamics, and the mathematical equation is delta Q is equal to delta U plus delta W. So we have defined a thermodynamical process in the way when a system changes its state from one to another. If a system changes its state from one to another, that process is called thermodynamical process. And the thermodynamical process is dQ is equal to dU plus dW. You can say that it obeys this equation, dQ is equal to dU plus dW. And it is found that there are different kinds of thermodynamical processes. There are different kinds of thermodynamical process. First one is an isothermal process. So in isothermal process, the temperature remains constant. Temperature remains constant. If there is no temperature difference, and last class I told you, internal energy change is identified by the change in temperature. Since in isothermal process, in isothermal process, temperature remains same. Temperature remains same is delta U equal to 0. Since delta T equal to 0. So what will happen? This equation will become dQ is equal to dW. The whole energy supplied to a system is converting into equivalent amount of energy. What? Energy supplied is completely converting into work done. Remember, it is an ideal condition. Another process is adiabatic process. Adiabatic process. What is an adiabatic process? Adiabatic process means there is no heat supply between the system and the surroundings. That means delta Q is equal to 0. So delta Q equal to 0. Then what will happen? Delta W is equal to minus delta U. Which means if there is no heat supply to the system and the system is doing the work, means its internal energy decreases. Which means the system is doing the work in expense of its own internal energy. Okay. Another one is isobaric process. In an isobaric process, the pressure remains constant. Isobaric process, the pressure remains constant. Another one is cyclic process. Cyclic process. So what is cyclic process? Cyclic process means a system is initially at the state A and it changes to B and from B to it going to C, and again is coming back to A. This is a cyclic process. That means it starts from a state and coming back to the same state, which means there is no state change at all. If there is no state change at all, there is no change in internal energy at all. So delta U will become 0. So delta Q is equal to delta W. Then again, delta Q is equal to delta W. Again, isolated systems are there. Isolated processes are there. Isolated process means again it is equal to isolated system. Generally, isolated system is defined as there is no interaction between the system and its surroundings. That means no work exchange, no heat exchange. So delta Q is also 0, delta W also 0. So obviously delta U also remains 0 there. So these are the different kinds of or one more thing, isochoric process. Isochoric process means the volume remains constant. If volume remains constant, dV remains 0. PdV will become 0. So dQ is equal to delta U. That means if there is no expansion or change in volume, then the whole energy supplied will be stored as its internal energy. So these are the different types of thermodynamical process: isothermal, isobaric, adiabatic, isochoric, cyclic process, and isolated process, isolated system. Okay, so that's all about thermodynamics. Simple chapter, simple concepts we have defined. So revise it. We'll meet in the next class.